Okay, so welcome everyone. Today we are very happy to have Damian Heisteeg from Harvard University. He's going to talk about finiteness and emergence of
Thanks very much. Thanks everyone for being here, for the invitation to visit. Really been loving Chicago for the last few days. It's a pleasure to tell you about some work we put out last December together with Matilda, Sanjay, Ethan, Conan, and Kai. And it's about trying to understand what kind of dualities really can show up in string theory, quantum gravity, and what can we really say about them, like in full generality, like what kind of groups can they be? Can they be tied to like some properties of the modular space, these sort of things. So to start with the kind of obligatory picture that you probably all know, if we take string theory, we have many of them, but we expect all of these to be connected through different kind of dualities, meaning that if we think of a string theory, we're somewhere in a field space and we go from one limit to another, we find that a different kind of description pops up. So this can happen in two ways. Either, well, we start in one theory, we really see a different theory pop up. But the case that I'll be focusing mostly about today is when you recover the same theory. Because in this case, it means that whatever field space we're working with, it means that it identifies one limit with another, and we should quotient out by this symmetry. And this means that that this field space really inherits some of the properties of these dualities, and that there's some kind of connection between the two. And that's what I'll try to zoom in on today. So to start things off first, let's do some basic examples. So let's take type 2a string theory, just one real scalar in this theory, and that's the dilaton. I'll parameterize it in this way such that phi going to minus infinity, well, that's where the string coupling goes to 0. That's where we have perturbative control. That's where we have 10D type 2a string theory. But as we go in the other limit, we find that, well, that's the strongly coupled region. And we understand that nowadays very precisely where there is a tower of the zero branes becoming light, which are the K modes of 11D supergravity. So here, we probably cannot say much through dualities because the different corners here are not part of like the same perturbative description, but we recover another theory on the other side. Yeah.
Why do you call M theory a weakly coupled description?
I'm not.
It doesn't have a coupling constant.
That's a fair point, but I can think of 11D supergravity, I would say, and that in terms of G Newton, and think of that supergravity as maybe not weakly coupled. Weakly coupled, I agree, is probably not the best term here, but at least I can make sense of it as a supergravity theory. Do you agree with that? Or not even at all? You think in 11D?
There is 11-dimensional supergravity, so I agree with that. I was just
Yeah.
countering your claim that there was always a weakly coupled description, because there is no weakly coupled description of M theory.
Okay, yeah, sure. Yeah, I agree. But then what I want to focus on is a case with self-dualities. So let's take type 2e string theory. Here, the real scalars are an axion field, C0, a string coupling, again, phi. And we know here that the supergravity theory has a global symmetry group, as all 2R. But we think of that as being broken down to the gauged subgroup, as all 2Z. One way to think of this is that, well, we have a charge spectrum of states, and if we ask these to be invariant in the global symmetry too, you only get this discrete subgroup. The other way you can think of it is you have instanton corrections, and these come with all the kinds of e to the minus 2 pi tau, but still an SO2Z will survive. What it does, it identifies these points through this relation. And I'm sure you've all seen this before. It restricts you to this standard fundamental domain, this keyhole-like domain, where we can generate it through two operators. We have the standard S duality, which sends tau to -1 over tau. And we have the standard T transformation, which shifts the axion field C0. And I'll get a little bit more later, connecting this with the finiteness properties and try to see why some kind of picture like this should hold up from the bottom up. But for now, I'm just reviewing the things that we already know. So what I want to connect these dualities to are to volumes of geodesic balls in moduli spaces. So say that we fix some interior point phi0 in the middle, we go out a distance delta. The geodesic distance that we compute here is just fixed by the kinetic terms, as that defines for us a notion of length for the moduli space. And then the basic question that I just want to ask you is, how does the volume of this region scale with delta? So we know many examples like the fundamental domain that I just showed you, that would be a constant number. I mean, just a finite number. The case before type 2a, we have a real line. Well, there it scales linearly. But what I'll argue for you at the end of this talk is that it should always scale polynomially. In fact, it should always scale like Euclidean space. Where, of course, if I take Euclidean space, where the geodesic balls would really be just balls, then you would have this kind of scaling with the dimension of the moduli space. And the claim I'm making is that it cannot be any faster than this. A different way, or maybe a related notion that's intuitive to the holographers around here, is that you can think of this in a weaker way as that the area of the boundary over the volume of the interior, that goes to 0 asymptotically, whereas for hyperbolic space, for instance, without any dualities, that would grow exponentially. And this would give you a finite number, therefore. Yeah.
Why is the volume of the moduli space finite? Well, what sets the finite?
Oh, it doesn't need to be finite. I mean, it can grow. You mean in a particular cases where it's finite, what causes it to be finite there, or in general, why?
But in general, it's not finite.
No, in general, it's not finite. I agree.
So this volume is infinite in general cases?
So
It's a growth as the
Yeah.
radius, you're looking at a big ball.
exactly. So it's the matter of whether I actually can go an infinite distance delta, of course, in this moduli space, and like in the real line moduli space that we just saw before. Let me go back. So here, I mean, it's just a real line. It has the standard flat metric, and here it would go as delta, and I could go all the way to delta equals to infinity, so phi equals to infinity and minus infinity. So there it would, yeah, you would have this infinite volume in general. Right. So,
Did you also fix the numerical coefficient in this inequality on the right?
so you mean the order 1 factor?
Yes.
Over here? No, I'll have a few comments about that, actually not based on our work, but based on work from another group that appeared, I think, last week. But in principle, it can be any coefficient for me. I agree. I mean, strictly speaking, for me, there could even be a log of delta. I just know that there cannot be a delta dimension of m plus a very small epsilon. That's what I mean by this twiddle here.
Why should this be true?
So I'll argue that at the very end, the intuition that we have is that I can give you the punchline already. So if this would be violated, so there would be an epsilon here, then you can have an infinite number, or then you can prove that you can have an infinite number of harmonic normalizable modes on the moduli space. And that you can think of as an infinite number of ground states for the theory in a certain way that I'll make precise. So this is the connection to the finiteness that
So the
if you
theory with the infinite number of ground state is terribly wrong.
that's the assumption there, yeah.
What's terrible about it?
Well, I think one way from maybe a more experimental point of view is that it would be impossible to start to match quantum gravity with experiments if there's infinitely many ground states that we could fit experiments with.
But if we in dimensions greater than 2 in QFT, when we spontaneously break a continuous symmetry, we do have infinitely many ground states.
Or you call that one ground state? Or you call
No,
I don't know what he's calling, right?
but you would say that you have an infinite number of,
If you have a U1 symmetry in 4 space-time dimensions and you spontaneously break this U1 symmetry, you have an infinite number of ground states.
but that's a U1 global symmetry.
Yeah.
But that, to begin with, we wouldn't expect in a theory of quantum gravity.
Well, I guess what I'm questioning, what's being implicitly questioned is the underlying logic that it's the number of ground states that's a problem.
Yeah. Yeah, I mean, I'm honestly asking, like, if you can consider like if you have an example of a quantum gravity, an effective field theory coming from quantum gravity, really, where you can have an infinite number of ground states.
Well, I guess I'm sort of turning it around in that it seems like gravity must be essential to saying one
Yeah.
thing about it. Since
Yeah.
in field theory, it seems to not
Right.
be thick.
Right.
So could you articulate maybe why
Yeah,
gravity
no, I
is
don't,
essential?
I actually, no, I don't think I have a very articulate reason for that, sorry. No, it's just yeah, more of a standard lore, I would say, in string theory. We expect a finite number of Calabi-Yaos. We know that we can only have finitely many flux vecua for a given Calabi-Yao. These sort of things all hint at finiteness, but I don't think there's a very good understanding of why gravity doesn't like infinitely many
What's the
ground states.
difference between 10 to the 500 versus infinite?
I mean, that's a great question. I mean, you might first ask nowadays. if
Revenge
you-
of the phenomenologists.
Yeah, I mean, I think that the 10 to the 500 is also being debated very much recently, and the question is more between whether it's 0 and 1. On that estimate for the number of de Sitter vecua in string theory. I mean,
Okay, you
Yeah.
will say that doesn't exist.
yeah, I think at that point it becomes more of a mathematical, like,
Why don't you keep
yeah.
going?
no, that's fine. I like the debate. I wanted to ask another question, which is, actually are infinite volumes of moduli spaces completely fine in EFTs? I'm not sure if that is, if there's any inconsistencies, if that would happen. But what we at least know nowadays, or what we know from string theory is that if we would fix an EFT, like we take our Calabi-Yau compactification, we have some finite cutoff, whatever we like. And we then ask, can we see the full moduli space, and actually find out that you don't. And the reason is that near any of these boundaries, there's this infinite tower of states becoming light. Say the Kaluza-Klein modes, say oscillation modes of the string. And that causes this quantum gravitational cutoff scale to come down. Moduli in a moduli dependent way, this amounts to some kind of exponential scaling, but let me forgo these generalities and actually just look at the example I showed you before. So take type 2A string theory. On one side, we know that the string mass is going down. On the other side, we know that 11-dimensional Planck scale is going down. So we know that if we would have, I mean, I now put it for the sake of the picture pretty high, like 0.5 and Planck. And then you would end up with some kind of finite moduli space like this. So as long as you put a finite cutoff, you wouldn't even see these infinite distances, or these infinite volumes, I should say, within the effective field theory with this finite cutoff.
I'm sorry, the point is that if you go outside that region, you have to add fields.
Yeah, the point is that if you would
Something
go
becomes
outside
light.
of this region, you would need to start including this tower of KK modes.
But are they massless or are they massive still?
They're massless, but
They're massive?
there
or
are too
massive?
many KK modes getting below the cutoff of your theory. That's the problem. And that is what this cutoff scale signifies. I mean, that particular cutoff skill is based on black hole physics.
What if I just looked at the effective field theory of the massless fields? Would I have a similar issue or not?
Well, but I mean, I was even just thinking of just the supergravity action with only the massless modes.
And outside this finite region, there are other massless modes?
No, there will be massive modes, but I'm saying that you could take this massless theory that you were asking for. You could, for instance, study black hole solutions in that theory, right? And I'm saying that if you would have too many of these light but massive modes, I'm saying that you couldn't trust these black holes semi-classically anymore. So for instance, it's decay into Hawking radiation, these kind of processes, these you couldn't describe within that EFT framework anymore. Does that make sense?
What confused me about this statement for years is that I could imagine setting all of these fields to 0. Why is it a problem not just setting them to 0 and working with the effective field theory? With the finite?
You mean like a consistent truncation?
No, I'm just saying to set this large number of light modes to 0.
But it sounds like they can be decay products of black holes that you make out of other
Yeah.
massless fields, so that's the problem.
Yeah,
That's fine. The black hole can be unstable.
yeah, I mean, it is unstable, but I'm saying that the unstable process by which it is unstable, you cannot describe that anymore. But I mean, this is not super important for my talk, so I can move on, but I'd be happy to discuss later. I just wanted to make the point about whether you see these infinite volumes or not, or expect to see them or not, based on cutoff skills and that sort of thing. So the plan for my talk today is I want to tell you first a little bit about dualities, a little bit beyond SL2Z also, like the standard type 2B dualities. I want to explain to you how much we can say about these dualities based on these compactifiability criterion. Like, can we say something about how the volumes grows and how that constrains kind of dualities that we see? And finally, I want to explain a little bit what I mentioned before about why we expect this compactifiability, this polynomial volume growth, Euclidean volume growth to begin with. So the typical stringy EFT that we would get looks something like this. We have some massless scalars, we will have some gauge fields. All the couplings here will depend on the moduli. And as we go to one of these boundaries, the expectation is that the tower of states is becoming exponentially light. And one of the things that we've learned recently in the swampland program is that we can understand this very precisely or at least that's the conjecture, the emergent string conjecture, that we actually can know this already from the standard way that we do string theory. Either this infinite distance limit is sourced by sending a string coupling to 0, or it's sourced by making extra dimensions large. But it can be nothing other than these two, so we can always make sense of it in the standard kind of picture that we have in string theory and compactifications. So now what is a duality here? So consider again this field space and say that we have 2 points and we can transform the Lagrangian, so all the couplings that I showed you before, and the spectrum between them by some duality transformation. So what this means is that we're reshuffling all these gauge fields. What we call electric and magnetic might change, but after we do all of this relabeling, we're really recovering the same theory as we go from one point to the other point here. So what that means practically is that if we take our moduli space, and let's know this dashed line is kind of like the fixed line of this operator, it means that we have to fold the moduli space and identify all of these endpoints, basically put them on top of each other. And one of the expectations is that, for instance, all of the non-trivial topology of the moduli space, so say whether you have contractible cycles, these sort of things, so that all comes from this picture, and that the original moduli space that we started from doesn't have any interesting topological properties at all. It's just like an upper half plane, nothing more.
What's the a priori definition of the original moduli space that we started from?
Right, so
I'm trying to parse this conjecture.
yeah. So the precise formulation that they came up with is that you should think of your so you have your electric and magnetic states, and if you know all your charged objects in the theory, you could unfold by these kind of quotients, right? Like if I know the full spectrum, and I know that if I went from there to there, maybe if I just would do like experiments with the theory, I wouldn't be able to distinguish this point from this point. But if I was able to track across what I call electric here, what I call magnetic here, and I go to the other side, then I would be able by that process to unfold the whole moduli space again.
But in string theory, this is often a gauged symmetry, yeah? The duality. So there might not be any parent theory that makes sense that is ungaged.
So let's take type 2D string theory to discuss it at that level. So you're what one would use to unfold the moduli space would be thinking about the spectrum of PQ strings. And then at least perturbatively, we would know in one corner what we call the fundamental string and what would be the other F1, D1 strings, right?
Okay, maybe I don't want to derail you if it's not your.
Yeah, I mean, your gravity theory itself has the larger moduli space. Right, I mean, supergravity itself will have an SL2R.
Yeah, is
Then I
the,
agree
is the
with,
pragmatic definition just
Yeah.
the
What the
group,
gravity-
the moduli seen by the supergravity versus the exact moduli? Is that what
think
we're
so.
talking about?
Yeah.
I think that's what we'll want to.
Yeah, that's probably the better way to put it, at least if you want to, like, yeah, if you want to use the supergravity framework, yeah, that's the best way to put it, I agree. Yeah, so the other way to think of dualities is as a zero form gauge symmetry. I'll just be thinking about, oh, sorry, yeah,
Can I ask you another question on the previous slide?
yeah.
It seems like the self-dual points in the moduli space are this line that you drew.
I mean, that's more for illustration, but yeah,
In principle, I can imagine my picture is many wormholes in the moduli space that connect different points that are not necessarily self-dual, just along some.
you're asking if it can have a more non-trivial
I'm just
topology.
saying the self-dual part of the modular space could be more complicated.
So it would be interesting to check, to discuss what you're having in mind there, because for geometrically, from moduli spaces of Calabi-Yau manifolds and these sort of things, it typically takes this very rigid devices are intersecting picture and it has no interesting topology. So I'd be curious to hear what you have in mind in detail there. Right. So at a generic point in the moduli space, we don't have these gauge symmetries. It's only when we go to one of the special points, like before I showed it as the middle line. Now I'm choosing to put these enhanced points for the symmetry at these boundaries where, for instance, if I shift tau to tau plus 1, then this would be the point where this symmetry is really restored as a gauge symmetry, but in the interior, it's not. And altogether, all I want to say is that this symmetry may not commute with that symmetry. So altogether, they will generate some non-abelian duality group like SL2Z, for instance. All of these symmetries are acting on the states that we have in our theory. So, for instance, particle states, deep range states, as long as their codimension is not too low, I mean, sorry. There will be a very nice linear action. This is like PQ strings, all of these things being relabeled. At codimension 2, things become more interesting because now as we consider, say, some kind of vortex, say, a seven brane or an axionic string in the theory, as we go around, the thing we can do is that, so this is in space-time, as we go around, we can choose a non-trivial holonomy, which acts by a duality transformation. So all of these objects we know very well in practice, but if you, for instance, take this no global symmetries in quantum gravity seriously, what that imposes on you is that all of these duality vortices really are there, that they're really finite tension objects in your theory. So as an example, let's discuss all of this at the level of type 2b. So we have this hyperbolic metric. SO2z is a symmetry group for that metric, an isometry group. We already discussed the action of the axiodilaton in this way on massless fields under which d branes and so on are charged. It acts in this nice linear way. But if we come to the 7 branes, so the codimension 2 objects, we have these funny objects that are charged under that implement a non-trivial duality transformation by themselves. So for instance, if we take the standard D7 brane, we would implement this D transformation that as we go around, we shift axion by 1. It's just an axionic string in that language, but you can generalize it by applying duality transformations into this more general SO2Z element. And the statement is that by fusing these things together, one can get all of SO2Z. Starting from the single D7 brane across different duality frames. Any questions on that part before I try to connect? This is also to give a little bit of background, and let me now get more to the point and try to really connect it to the volume growth of the moduli space and what this says about the duality group itself. So I already introduced for you this notion of compactifiability. But how does this precisely compare to what the typical moduli spaces look like, and how do they really satisfy this criterion? So for me, an intuitive way to think about all of this is to connect it with the curvature of the moduli space. Why do I say that? Well, I know that positively curved spaces will be compact, finite volume, think of a sphere, these sort of things. If I have flat spaces like Euclidean space, of course, I get these volume growths that we already saw. But if I have negative curved spaces, that's where things can get really dicey. Because there, for negatively curved spaces, you typically would expect an exponential volume growth. So the only way out there is having many dualities, but let's talk about the flat moduli spaces first. So take 10D type 2a, we already discussed it. We find a linear growth. That's not really the only example of that type. If you would take empty line bottle, a moduli space would be R2 mod Z2. So there you would even get the quadratic growth. It's an interesting question. What is the maximum power law that you can get? Can you really, for like the Calabi-Yau manifold with H11 equals 490 or something, could you really get like a delta to the 490 or not? I don't want to talk about that. For the negatively curved spaces, on the other hand, it's much more interesting what the dualities are doing, because even though naively you would expect an exponential volume growth, you also have so many dualities at the other hand that identify so many copies that actually only a finite number remains. So for the standard fundamental domain in the upper half plane, it's just pi over 6. If I would take M theory on tori, you have some of these symmetric moduli spaces. These are also all known to have just a finite number as volume, as long as you divide here by SOPQZ. So really the full duality group there, the U duality group. And even more strikingly, if I would look at the vector multiplet sector in a 4D n equals 2 supergravity that you get from a Calabi-Yau manifold, even there, it's known that the volume, proven by mathematicians, that the volume should be finite. So it's really these dualities doing a lot of the work for you.
But most moduli spaces have some regions of positive and negative curvature. They're not just homogeneous spaces.
Right. So people have indeed been working a lot on trying to understand these positive regions a lot. So that's why I put the asterisks that I'm calling them negatively, but I just mean that they're mostly negatively curved. And it's indeed a work in progress that people are trying to understand better where these positive divergences come from. And the lesson, at least, that has been taken away from that so far is that it comes from additional field theory sectors in the theory. So that precisely in these limits where you have the positive curvature divergence, that's a limit where you're decoupling gravity from that field theory state or from these field theory states. Yeah, so for instance, well, I'll comment on that in a little bit more detail, like in a particular example.
Just a question. I'm trying to understand how this volume is actually calculated. Are you doing an integral of square root of minus the determinant of the metric of the moduli space? And what are the boundaries of your integral when taking some specific example?
So I'm saying take 1 over tau 2 squared, for instance, in the upper half plane as a metric. And I'm saying integrate over this region. And if I integrate over that region, I get that the volume is pi over 6. There's a nice way that actually, if you want to do it, you can do it really through a contour integral. But let me not get into those details. Where you just see that this is really the pi over 6 circle, and this part cancels out that part. But that's what I'm talking about.
It's always the case that the volume is finite. I think you told me before that in some examples the volume is infinite.
Yeah, I'm just saying that
And then
I'm just explaining. Yeah, I'm just explaining the nice case where it's a nice finite number.
But in the cases where it's infinite, how do you determine the upper boundary of the integral? Or in other words, how do you regularize the volume?
Well, I did that by construction, right? Because I choose an initial point and I go out the distance delta. So that fixes the normalization that you're asking for. It's because I'm looking at the geodesic ball with some origin that I pick myself, and then I only go out in that moduli space a distance delta. That fixes the normalization, what you're asking for.
So this is all sort of Clavier flat space inspired stuff.
Yeah, it's all Clavier inspired stuff.
So
Yeah.
if you went to sort of ADS cross something positively curved, which had a moduli space in that, are there just no interesting examples there? I guess like it may be
Well, I mean, if you would do ADS 5 times S5, you would still have some.
definitions, right? of the
Yeah,
similarity.
you would still have the standard upper half plane with SO2Z.
But then you
I
map
think-
it back to a CFT statement about what you're not allowing for holographic CFTs.
I see what you're saying. Yeah, I mean, it's a claim about the space. I think it's a claim for UV complete CFTs and what the space of marginal deformation should look like for them. I think there is indeed an analogous statement, and I think often you can map the kind of statements that I'm making here about curvature of the space of marginal deformations. There is an equivalent notion there. Yeah, but I don't recall it from the top of my head. So after all of these good examples, let's finally look at a bad example. So what if I would have had type 2b and I would have not known what the full duality group is, and I only recognize this tau going to tau plus 1 shift symmetry. And then I would have some fundamental domain that only looked like this strip. I fix some point in the middle and I go out the distance delta. Well, in terms of the e to the phi, that corresponds to an e to the minus delta up to e to the delta. And if you compute now with the hyperbolic metric the volume of this region, you find that it is proportional to e to the delta. So it diverges exponentially. And actually most of that volume is really sitting here. So it's really coming from this part of the integral down there.
Your measure still has the 1 over tau 2.
Yeah, this is just with the metric that has to 1 over tau 2 squared. Yeah, it's just integrating that metric from here to there. Yeah. So by our logic, it's not compactifiable. But what does that really teach us about the duality group, right? I just gave you an example of a duality group and I say it doesn't fit with our volume growth criterion, so it doesn't work. But what can we actually take away from this lesson? And one of the things that I'll argue for you more generally in a little bit, but one of the things that you notice, sorry, let me actually skip this part. Why? I can comment on that other work later. But Siri just triggered my laptop. I'm sorry about that. It's
Always listening.
yeah, it's always listening, and it didn't allow me to click through my slides anymore. Sorry. Okay. So the criterion that I'll argue for you in a little bit is that the duality group should have a semisimple representation. So what do I mean by that? I mean that the full spectrum of states can be decomposed into just a sum of irreducibles. So for instance, in type 2b here, I mean that I can think of all these sectors of PQ strings, D3 branes, 5 branes separately. And more intuitively in a picture, what it feels like to me is that in a semi-simple case, you can have that dualities, if they can add some of B charge to the sector A, you should also be able to add some of the A charge to B. Whereas in a non-semi-simple case, you would have dualities that only can add A charge to B. So why do I picture it in this way? So if you look at that bad example that I showed you before, you would have a situation where you have B charge 0, 1, and this monodromy is able to add it, or this operator, this T transformation, is able to add it to the A charge, but there is some non-democratic way in which it's working, and semi-simplicity is a way of demanding that it has this democratic way of distributing dualities, the charges across dualities. So can we make this more precise? Like why would we think these two things are connected? So for that, I want to fix now, use a little bit of Calabi-Yau inspiration. So what do we know for Calabi-Yau compactifications on a full string theory on a Calabi-Yau threefold? And we have the vector multiplet sector that's encoded in the geometry of this Calabi-Yau manifold. And in particular, very nice things like the monodromy group associated to the moduli space, we can identify as the electromagnetic duality group of the supergravity theory. So if we can say something mathematically about this monodromy group, it means that we can say something about the duality group. So then it's interesting that there is this very general proof that doesn't even need a geometric description. It just needs an abstract set of periods, so an abstract kind of geometric setting, where if you assume that the moduli space is actually compactifiable, from that they can prove that this electromagnetic duality group should be semisimple. Here they don't mean exactly what we mean by compactifiable. They mean something slightly stronger, specified to complex spaces also, which is a risky open in a compact analytic space. I don't want to go into too much details on that point. And we already know that, for instance, from the geometric setting, that all of these moduli spaces really should be compactifiable. But so why is that? That if I assume this compactifiability of the moduli space, how could that say anything about the monodromy group, right? Or about the duality group? So let me at least sketch you the proof in a slide.
Sorry, before you go back to that, I want to make sure I understand this Todorov result that you keep quoting.
Yeah.
So the Calabi-Yau 3 moduli does have singular points, like conical points.
Yeah.
Does it claim that those are like integrable in the volume, or that somehow you cap them off? What?
So you go to that point. The volume contribution.
The volume
that is
integral
finite.
is finite.
Yeah, it's finite.
Even though the curvature is not.
The curvature is not, but the integral of the curvature would be. Yeah, the curvature is integrable, even though it diverges. Yeah.
I see. Okay.
Yeah, exactly. Yeah, I'm really doing the naive thing and really.
Totally get it. Yeah.
So now where does this semi-simplicity come from? So let me give you a slightly different, more formal definition of semi-simplicity. So it means that if I have some subspace, so I have a vector space that these monotomies, these dualities are acting on, let me take some subspace and that subspace is preserved by the monotomies. So I just mean that if I act with any of these duality operators on V, it will give me back an element of V. That's what I mean by invariant. Equivalently, you could think of some suitable sub-representation. And if you want to show that you now have like that W gives you a semi-simple representation, it means that there should be a complementary V prime such that the sum of them is the full thing. So the question is, how can we determine this V prime? And so the most natural way that one would do it is you just do physics, you identify a suitable positive definite inner product, and you just take the dual of V. That's your V prime, that does the job. It just needs to play well. The one thing that you do need to check, of course, is that this inner product plays well with the monotomy. But let's get into that later. So the first point is, the standard thing that you would have proposed is, well, let me just take the wedge product on this manifold and take that as a definition of this inner product. But that actually doesn't have the right signature. Actually, let me show you all of it in an example to connect it with the good thing. So for instance, for type 2b, for the standard upper plane, this would be the first pairing, and that wouldn't be positive definite, so it's not possible to take a good orthogonal complement. But the good pairing is the one that we actually already know. For instance, it's the one that we use to compute tensions of PQ strings. And in principle, that would work, but the problem is that it's moduli dependent through this Hort star that's in there. And then the whole point of assuming compactifiability is actually that you can use this metric to show this semi-simplicity, so to get this V-per. I don't want to get into the details of that part, but I think intuitively, yeah. Sorry, the point I just wanted to make is that there is a very natural way to unpackage this condition and think of it as states and orthogonal states. But the suitable thing is moduli dependent, and it's precisely the kind of things that these mathematicians assume about compactifiability allows them to show that this moduli dependent pairing has the right properties for semi-simplicity. Sorry, any questions here? So let me in the last 10 minutes or so.
So the proof there, so this was shown for Calabi-Yau 3 folds, was it also shown for 4 folds?
Oh, actually, this proof is not even for Calabi-Yau manifolds. It's just for theorist for any manifold. Yeah. Yeah, it's not even about Calabi-Yau 3 folds per se. It's just what I wanted to fix as a setting to discuss all of this on. Yeah. And it's part of why one might hope that it holds more generally. Yeah. So can
The
we?
total result about finiteness of the moduli space is specifically for 3 folds.
It's no, I don't think so actually. I think it's for any dimensional Calabi-Yau manifolds though, whereas the result I showed you just before goes even beyond Calabi-Yau.
Yeah. Okay.
Yeah. Let me actually, how until how late is the seminar usually? Like until 2:30?
So take at least till 2:40.
Okay. So I wanted to now, given all of these general statements, can we, like in very particular settings, say a little bit more about what the monotomy groups, these duality groups look like in practice? So first, a little bit of background. So this is the most simple kind of moduli space you could consider. It's just a sphere with 3 punctures. It's the original moduli space that was studied for the quintic in the first days of mirror symmetry. There's one point that we know very well. It's the large complex structure point. This is the point where we decompactify the theory from 4D to 5D through this mirror tower of D0 branes. There's the gonifald point where we just have a finite number of hypers that is becoming massless, and that is causing these kind of positive curvature divergences, but only locally, close to that point. And then depending on the example, because there are 14 of this type, depending on the example, you find different kind of singularities at infinity. So you can have, again, a large complex structure or a gonifald point, but you can also have a Leno-Ginsburg point. For instance, like in the quintic, this would be its special Z5 point. Or you could have what's called as a K point. I won't go into these kind of examples in more detail, but there you would also have an infinite distance limit. And now, one takeaway that you can have immediately is that if you look at the typical form of the monodromies, they already fit with this semi-simple structure that I described before, because this is a fully lower triangular matrix. And this gonifald monodromy is precisely mixing up the heaviest and the lightest state under the first monodromy. So it's really mixing up everything in the kind of picture that I tried to show you before. So it's manifestly semi-simple in that way. Let me skip this part.
Can you see that the matrix is semi? Can you see from the matrix that the semi-simple structure?
I mean, in this case, I think so, because that's the representation that you, I mean, yeah, because that's the representation that you're looking at if you look at the matrices, right?
The triangular nature of the matrix?
Yeah, that's what I meant, yeah. But okay, so can we actually say a bit more about the duality group apart from the matrices that generate it? So in type 2b, there's this very nice way to think about SL2Z, which is in math terms known as a free amalgamated product. And that's just a fancy way of saying, well, I know that there's a Z4 symmetry, I know that there's a Z6 symmetry, and the only known relation between them is that the square root of one and the cube of the other are equal to -1. And apart from that, there are no relations between any of the generators. And that is what would constitute such a free amalgamated group. So this free amalgamated structure also shows up in the Calabi-Yau manifolds, but not precisely in a super nice way that it shows up here. So here you really have that you have some finite distance, even finite order monodromy points, and with that you can generate duality group. But you might hope that, well, maybe I can even do that for these Calabi-Yau manifolds, but that turns out not to be the case. So 12 years ago or so, these mathematicians actually computed all these monodromy groups, and they showed that these were again this free amalgamated structure, where you have either Z times Z, Z times ZK, or you have this annoying amalgamation here by the Z2, but that Z2 is nothing more than -1 again. So these first monodromies here are always a gonifald point. This one can be large complex structure of gonifald, and these can be of Leno-Ginsburg type. And already from this, you see that there's so many Z's around. I cannot just have finite order monodromies. I really need infinite order monodromies. Right. So this is on the left. I just give the precise Calabi-Yau as a hypersurface, and then I give all the monodromy data that I just described to you. The interesting thing is that all of these cases actually have an infinite order monodromy group. Sorry, of infinite index, I mean, in SP4. Even though they have a finite volume, so already that kind of condition doesn't hold in general. There's still a mathematical notion of that it's dense in SP4. But really the point that I want to drive home here is that in general, duality groups cannot be generated by finite order monotomies, just by those, or even by monotomies associated to finite distance points. Because there are just examples where you might need an infinite order, infinite distance monotomy to generate everything. So this kind of logic that maybe you could generate everything from the finite distance bulk of the moduli space, that at least doesn't hold. And that's the one takeaway from this example. Sorry.
What the type refer to?
Oh, the type refers to the type of singularity at infinity. So for the quintic,
Structure or.
exactly. So for the quintic, this would be its Landau-Ginzburg point. That would be its C5 point. That would be what characterizes the quintic in this way. But that point could also be large complex structure or conifold,
Oh, I see.
or this K point type. So that's by which you, yeah, that's what I just meant by type. And then you see that there's this one row where you would have a second LCS point. So you mean you have two LCS points and one conifold point, and you use one of the LCS points and one of the conifold points to generate the full monotomy group.
Is there a full classification of the singularities of the Calabi-Yau manifold?
Yeah, there is.
Which is given by.
I mean, I'm giving you just a classification at the level of one modulus, but there is even a more general classification. And this kind of classification is known as like limiting mixed Hort structures. But there is a framework for that, yeah.
What is the index in this context? What is the definition of index here?
Oh, sorry, the definition of index is just that I skipped over that slide because I was hurrying too much. I just mean it's the order of the group inside SP4. That's what I mean by index. Yeah, sorry, I should have. Yeah, it's not on this slide. Sorry. Yeah, it's this. And that's yeah, just an artifact of that. The matrices. You would decompose typically SP4 in this way, but they act on the coordinates here, but these magnetic dual periods down there. So somehow, because of this slightly different structure here compared to SL2, you can have infinite index for the duality group, even though everything is finite volume, as you quotient by the duality group. Whereas normally you would think that you get the order as a multiplicative constant in the volume.
What is the intuitive meaning of an infinite index?
I mean, it's just that I can have, to generate this coset, I just need I have an infinite number of elements in that coset. I mean, where it's precisely coming from here? No, let's discuss that afterwards. All right, so let me try to finish in the last 5 minutes or so. So with this bottom-up argument, so I am taking finiteness as a premise here, and I do assume that it's there. We can debate later about whether we expect the number of ground states to be finite or not, but let's work on this assumption of there being a finite number of ground states. So what can we say then? Okay, so this was part of the motivation, but I think we already talked about this a little bit. But so let's take, what I want to do is let's take our d-dimensional theory of quantum gravity. Let's assume that we have SUSY, and let's compactify it further on a d-1 dimensional torus, such that we land on a 1D supersymmetric quantum mechanical system. So this SUSY setup in 1D is very well known. We know that the ground states of the quantum mechanical theory can all be mapped to p-forms on the Calabi-Yau manifold, not on the Calabi-Yau manifold, sorry, on the moduli space of the setup of the. So now the question is, can we relate the growth of the volume to this spectrum of forms, of modes? And then there is, if I consider a space of dimension 2k, and asymptotically its metric has this kind of form, then precisely when this epsilon would be bigger than 0 is when there would be infinitely many harmonic normalizable k forms for a space of dimension 2k. So precisely when the volume would be growing faster than Euclidean, so delta more than the dimension of the space, is when you would have an infinite number of ground states. So what does that look like for type 2b? So let's say that we would have done type 2b, we wouldn't have known about the duality group, then precisely this spectrum of one forms is given by the one forms that I wrote down for you here, labeled by this n, which all are massless, so all are harmonic really. Now a question you may ask is, well, but you started with your higher dimensional theory, you compactified on a torus, but what about the torus moduli, right? Well, there's an easy way to make sense of that, even though in general I agree with you that there would be a lot of mixing because loop corrections, instantons, all of these sort of things guaranteed as this wouldn't be a factorized moduli space. But there's one limit where I could make sense of this. And the only point that I want to make here is that if I want this full moduli space to be compactifiable, well, that I have an argument for. And I'm just saying that therefore this particular corner should also be compactifiable. And at least in that particular corner, I know that this semi-direct product is a normal type of product.
What?
Yeah.
Kind of stupid.
Yeah, yeah.
You compactify down, you get supersymmetric quantum mechanics, but it's still coupled to 0 plus one dimensional gravity.
Yeah.
So does that not change the story in any way? Because this story sounds like the story of just SUSY quantum mechanics.
Yeah, yeah. You're saying that whether the gravity sector does something to the ground state counting and these sort of things?
What do you mean by ground state? Yeah.
Yeah.
Because these are local wave functions.
Yeah, that is a fair question. Yeah, I probably what I should say is that I'm also considering a limit where gravity is decoupled to make sense of just this quantum mechanical theory.
This was my question, that you need to take the string coupling to 0 as well in order to make this statement.
I see, that's fair. Yeah. Yeah, I think to honestly study this 1D quantum gravity theory, you should also take the gravity into account. It's just based on this observation with just the quantum mechanics sector of that production. So let me sum up. So I think, or at least I hope that I've convinced you a little bit that this compactifiability of moduli spaces, so all of these polynomial volume growths demanding that, or Euclidean volume growths demanding that for a moduli space gives an interesting way to say something about what the structure of the duality should be, at least predict some of the dualities, but also say something about what they look like in the form of this semi-simplicity of the representation. I think it would be interesting to see if there's just a normal independent quantum gravity reason why duality should be semi-simple. So far, we've only been able to tie it to this moduli space feature. Would be interesting to have an independent argument. And of course, similarly, it would be interesting to extend all of this in the presence of scalar potentials. Can we say something more about dualities in these sort of setups? But let me not save you with these speculation and just thank you for your attention.
In the absence of the semi-simple structure, you showed an example where the volume, the moduli space grows like e to the delta. Is there some argument that the maximum growth is e to the delta and not say super exponential?
Yeah, you mean like a double exponential e to the delta? I mean, we're arguing, you're asking whether the naive moduli space without dualities, whether you could constrain that as well. I don't know. Good question, though. I think at least geometrically speaking, like all these standard type Muller type spaces, that there you only expect an exponential growth, not a double exponential.
So just to clarify, so this, when you said that there's equality to the volume, so it's for any submanifold of the moduli spectrum satisfied. Yes.
Yeah, that was at least the logic there, yeah.
Okay, so any subspace I take. Just an equality.
If there are no more questions, like.
Okay. Are you busy now, or do you want to start now? Yeah, I'm just gonna be off then.